Okay, so in our last video, I explained what a dipole moment was and that certain molecules are polar when their dipole moments cause them to have like a congregation of electrons at one end and no electrons at the other end. So a molecule would have a whole bunch of electrons, whole bunch of electrons at one end and not any electrons at the other end. And so this would be a polar molecule. And that's because of the electronegativity of the atoms pulling the electrons from one side of the molecule to the other end of the molecule, and all the electrons end up over on one end of the molecule. So that's polar, and those are caused, each one of these uh, pulls of these electrons to the ends are called dipole moments. So that's what a dipole is. Now that leads us to our main topic, which is intermolecular forces. And inter means between, and the molecular part means molecules. So intermolecular forces just mean the forces between the molecules. These are how the separate molecules come together to make one thing. Just like in a glass of water, like here's your glass, and then inside your glass you have a whole bunch of water. And so the water is H2O, right? So H2O, H2O, you have a whole bunch of H2O molecules all making up this water. But how do these H2O molecules connect together, hook up together, so it makes this uh, glass of water, so the water all stays together? It's not just individual. If you pour the water on a table, you're not just going to get individual H2O molecules in little dots all over the table. You're going to get a puddle. So how do these H2O molecules connect together to make up what we know as water? So intermolecular forces. We have the ion-ion interactions, and that just means a molecule made from an ionic bond interacts with another molecule made by an ionic bond. We have an ion-dipole interaction, which just means an ionic bond molecule interacts with a dipole molecule, which the dipole molecule, as we said before, are the polar molecules. We have hydrogen bonding, and which is actually a form of a dipole molecule, but we'll get into that later. And then we have dipole-dipole interactions, where uh, a dipole molecule interacts with another dipole molecule, and that's how they stick together. And then we have London dispersion interactions, the London dispersion force, which is when a what's called a momentary dipole, a normally nonpolar balanced molecule or atom, momentarily turns into a dipole for whatever reason, and this usually happens with gases, and that hooks up to another dipole or another molecule having a momentary dipole interaction, and they hook up together. So that's London dispersion, but I'll get into explaining that in a little bit. So ion-to-ion interactions, again, we're talking about intermolecular forces here. And intermolecular forces are the forces that connect the molecules together. So what forces connect which molecules together is what we're looking at. And right now we're talking about ion and ion interactions. So this is when a molecule made from an ionic bond is connected to another molecule made from an ionic bond. And we can discern which one has the higher melting point by just multiplying the charges on each of the ions. So as you can see here, we have aluminum nitride, that's aluminum and nitrogen, and magnesium and oxygen, magnesium oxide. So aluminum and nitrogen breaks down into aluminum and nitrogen. And if we look on the periodic table, aluminum is over here. So aluminum would be the metal, and nitrogen would be right here. So nitrogen would be the nonmetal. And aluminum has, in its ionic state, the ion aluminum has how many charges? Well, it's going to have 3 positive charges because aluminum will give up 3 of its electrons. And you can tell that because we're in column 3, 3A, and so this column right here, column 3A, means that everything in this column is, if it's an ion, it's going to have a positive 3 charge because it has a tendency to give up 3 electrons. And then for nitrogen, nitrogen is over here, and nitrogen's charge is going to be a 3 minus because nitrogen has a tendency to take on 3 extra electrons because nitrogen is 3 columns away from the 8th column. So 1, 2, 3. It's 3 columns away from the 8th column, so that means it's going to have a charge of negative 3. So the aluminum is going to have a positive 3 charge, and the nitrogen is going to have a negative 3 charge. So that enables them to come together and make aluminum nitride as a balanced molecule because the plus 3 and the minus 3 cancel each other out. So the total charge of aluminum nitride is 0. But so if you keep those broken apart, we have aluminum, which is 3 positive, and nitrogen, which is 3 negative. And if you multiply those two 3's together, forget the negative and the positive, just take the number itself. We have aluminum has a 3 charge, nitrogen has a 3 charge. Yes, it's negative, but we're ignoring the signs. We're just taking the numbers, the 3, and you multiply them together, you get 9. Okay, now let's take that in comparison to magnesium oxide. Magnesium and oxygen breaks down into magnesium, which has a 2 positive charge, and oxygen, which has a 2 negative charge. So if you take the 2 from the charge of the magnesium and the 2 from the charge of the oxygen, again forgetting the negative and the positives, we're just taking the numbers, we get 2 times 2 equals 4. So aluminum nitride has, if you multiply their charges together, you get 9, and magnesium oxide, and if you multiply those charges together, you get 4. So the one with the higher number, when you multiply the charges together, that's going to be the higher melting point. So we can also say the higher boiling point. Same thing, higher boiling point, higher melting point. So because if you take the charge of 3 of the aluminum and the charge of 3 of the nitrogen, multiply it together, you get 9 compared to the magnesium oxide, which those charges multiplied together is only 4. So when you compare ion to ion interactions, whichever has the highest number when you multiply the charges together from the ions, that's the one with the higher melting point. Now, here is an ion-dipole interaction, and this is when an ion and a dipole molecule interact so they bond together. So as you can see on the left, We have water, which is H2O, which is a dipole because on the O end of it, has a partial negative charge. It's right there. And then on the H ends, there's a partial positive charge on that end of the molecule. So this is definitely a polar molecule. And here we have an ion over here. We have a sodium ion, and that's Na plus. And the opposites attract, remember. Just like an ionic bond, you get um, an ion of an element that has a positive charge will bond with an element that has a negative charge. Well, just the same way, we'll have this ion with a positive charge that's going to bond to the negative charged end of this polar molecule. So the sodium ion, the Na plus, is going to be attracted to the negative end of the water molecule, which is by the oxygen. So you end up getting, here's a water molecule, and you end up getting a sodium ion that bonds on the O end, the oxygen end of that molecule. It's short but sweet. That's simply an ion-dipole interaction. Now we can take this a little bit further, and on the right we have an example of dissolving NaCl in water, sodium chloride. So we have NaCl, and if you break those ions up, the Na turns into an Na positive or an Na plus. It has a positive charge, and the Cl has a negative charge. Well, and then you put that with water with this polar molecule. Well, the Na that has a positive charge is going to be attracted to the negative charge end of the water molecule, which is the oxygen end of the molecule. And the negative chlorine ion is going to be attracted to the positive end of the water molecule where the hydrogens are. So if you have a water molecule like this, and you bring NaCl into the mix, the Na, because it's positive, is going to stick to the negative oxygen end of the molecule, and the Cl, which is negative, is going to stick to the positive hydrogen end of the molecule. And this is how salt is dissolved in water. The water comes in and it breaks up the NaCl, which is salt, and it breaks apart those two ions, the Na and the Cl, and the Na part, the sodium part, sticks to the oxygen end of the water molecule, and the chlorine part sticks to the hydrogen end of the water molecule. And that is how salt is dissolved in water. Now, a dipole to dipole interaction is when two molecules that are polar, so therefore they have a dipole moment in them. When two dipole molecules are bonded together, how are they bonded together? Well, the positive side of one is bonded to the negative side of the other one because opposites attract. So don't forget that. Opposites attract. The negative end of one molecule will hook up with the positive end of another molecule and vice versa. The positive end of one dipole molecule will hook up with the negative end of another dipole molecule. So let's take, for instance, carbon monoxide, and we have two molecules of carbon monoxide here. So carbon monoxide uh, is just CO, is just carbon and oxygen together, and oxygen has more electronegativity than carbon does. So oxygen is going to hog all the electrons over here. All the electrons are going to be going this way toward the oxygen and leaving the carbon without any electrons. So it's going to be polar. This molecule is going to be polar because of the dipole interaction. And remember the carbon end is going to have this little fancy lowercase d for lowercase delta with a plus on it to say that the carbon end of this molecule is partially positive, and the oxygen end of this molecule is partially negative. So if you take two of these molecules, two carbon monoxide molecules, you have the carbon with the partially positive end, and then the oxygen has the partially negative end. And then you have another molecule of carbon monoxide. That carbon end, which is partially positive, is going to be attracted to the partially negative end of the other carbon monoxide molecule. So this negative end with the oxygen is going to be attracted to the positive end with uh, the carbon end of the molecule, and that's how they're going to connect. That's how they're going to bond together and hook up. Now let's look at, on the right, let's look at another version of this, which is hydrogen bonding. And hydrogen bonding can be in a whole category in itself, but it is part of the dipole-dipole interaction. But we can also consider the hydrogen bonding a separate kind of interaction because it's only when a hydrogen is connected to a fluorine, an oxygen, or a nitrogen. So I always remember hydrogen, phone, home. So phone, F-O-N. So the hydrogen has to either be connected to an F, or the hydrogen has to be connected to an oxygen, or the hydrogen has to be connected to a nitrogen, and that's it. Those are the only times you'll see a hydrogen bond are these connections or these hookups right here, just with a fluorine, an oxygen, or a nitrogen. So let's take water, for instance. We have, here we have the water molecule. Here's the O, which is partially negative, and it's hooked up to two hydrogens. So the hydrogen end is partially positive, and the oxygen end is partially negative. And then we have another water molecule. So we have an O that's partially negative, and the hydrogens, which the hydrogen end is partially positive. Well, the O, the partially negative end, is going to be attracted to the partially positive end of the hydrogen in the other water molecule. So water, as I was saying in a previous video, if you have a glass of water, this water is all H2O, right? It's just water. So this is all just H2O molecules. But how come when you pour the water on the table, it doesn't just break apart? It's not just individual H2O molecules on the table. Instead, it's a puddle. It's a puddle of water. Why do these molecules stay together? Why do these stay cohesive in this liquid form of water that we know it? Well, because the positive um, ends, the hydrogen ends of the water molecule are positive, and they connect because opposites attract. Don't forget that opposites attract. They connect to the partially negative part of the molecule of the other water molecule, which is oxygen. And so that's how they bind together. And so both of these are examples of dipole to dipole interactions. So finally we have London dispersion forces, which are also called van der Waals forces. In London dispersion forces, these are forces between all the molecules, but they're the predominant force found in nonpolar molecules, because the molecules that don't have a dipole moment, they remain neutral. Their electrons are evenly spread out all around the nucleus, so they're nonpolar. And so these London dispersion forces are what enable nonpolar molecules to stick together. And they're based on temporary dipole moments of the neutral molecule. So pretty much what this is saying is that You know how I just explained how dipole or polar molecules stick together with dipole-dipole interactions. The way nonpolar molecules stick together is they temporarily turn into a dipole atom or a dipole molecule, and that induces their neighboring atom or molecule to also turn into a dipole atom or molecule. They also have a dipole moment, and then that enables them to bond together. So I'll show you what I mean. First, we have, say we have fluorine. We have an atom of fluorine, just a normal atom of fluorine, and fluorine has 9 electrons total. It has 7 electrons in its valence shell, but it has 9 total. And the electrons are constantly orbiting around the nucleus. So electrons are in constant motion, uh, going around and around the nucleus of this fluorine atom. And then occasionally, because electrons orbit around the fluorine randomly, occasionally it just so happens that all the electrons kind of bunch up and end up on one side of the fluorine atom. Um, this is just temporarily, and then they'll move, and then they'll go back to being evenly distributed around the nucleus of the atom. But just occasionally, the electrons all moving around the fluorine, it just so happens that they end up uh, on one end of the fluorine atom. Well, so what that causes is what's called a temporary dipole moment. So for just a short period of time, the electrons end up all on one side of the nucleus of the fluorine atom. So that makes this side of the fluorine atom partially negative, and then the side where the electrons are missing, is temporarily positive or partially positive. So this is a temporary dipole fluorine atom. Then what happens is this temporary dipole, this fluorine atom that we were just talking about, it just so happened temporarily the electrons all bunched up on one side. It turns into a temporary dipole, and then it runs across another normal fluorine atom where the electrons are all evenly dispersed all around the nucleus of the atom. So those two meet. So what happens? What does that temporary dipole do to this normal evenly dispersed electrons around a fluorine atom? Well, what happens is, since this temporary dipole has a partial negative charge over on this side where all the electrons are, and a partial positive charge over on this side where none of the electrons are, well, that positive temporary partial positive charge attracts these electrons over here on the normal fluorine atom, and it gets them to all move to one side of the fluorine nucleus, because the electrons being a negative charge, remember opposites attract, and these electrons are all negatively charged, so they are attracted to this partial positive charge of this other fluorine temporary dipole over here. So that causes the second fluorine atom to also turn into a temporary dipole. So it causes all of this fluorine's electrons to also bunch up on one side of the atom because it's attracted to the positive partial positive force of this of the first temporary dipole that we were talking about. So now the side with the electrons on it have a partial negative charge, and that partial negative charge and the partial positive charge of the first fluorine atom, they bond together because opposites attract. So the positive and the negative bonds together, and those two fluorine atoms end up sticking together. And that is what is meant by a London dispersion force as an intermolecular force. This is how atoms, especially gas atoms, or atoms in the gaseous state, um, will bond together and can stick together.